Imagine a wind so violent it can turn a piece of straw into a bullet capable of piercing solid steel. On May 3, 1999, humanity witnessed exactly that. A monster emerged in Oklahoma that shattered our understanding of physics, registering a speed that seemed mathematically impossible for our atmosphere. The actual number shouldn't exist. The wind didn't just break records, it defied everything we know about atmospheric boundaries. We aren't talking about a standard hurricane. This was a force traveling at 318 miles per hour. To put that in perspective, that is faster than a Formula One car at peak performance, and fast enough to rip asphalt straight off the highway. Scientists around the world were genuinely baffled when they saw the radar telemetry. How could a planetary atmosphere even generate that much kinetic energy without tearing itself apart? To understand why this is so bizarre, we have to look at normal science. Typically, winds are created by pressure differentials, air moving from high to low pressure. A normal, severe tornado might clock in around 150 miles per hour. That's enough to throw cars. But atmospheric friction usually acts as a natural speed limit, capping how fast air can physically slide across the Earth's surface. According to standard meteorological models, the thermodynamics of that day should have capped the wind speeds well below 250 miles per hour. But reality had other plans. It's 1999, Bridge Creek Moor, Oklahoma. Meteorologist Joshua Werman and his team were operating a mobile Doppler radar system called Doppler on wheels. As the supercell storm darkened the sky, the radar began feeding data back to the truck. The numbers started climbing, 250, 280, 300. The team thought it was a software glitch. They recalibrated the instruments in real time while the storm roared outside. But the data didn't drop. Instead, tension spiked as the instruments locked onto a localized vortex within the main tornado. They had just recorded a wind speed of 318 mph, $PM 20 \text, mph per dollar. How did it happen? The main tornado had spawned tiny, hyper-intense sub-vortices, essentially mini tornadoes spinning inside the main funnel. Think of it like a playground merry-go-round. If you are running on the ground, that's the storm speed. If you jump on the spinning wheel and sprint in the same direction, your total speed combines. This compounding velocity is what broke the theoretical speed limits of Earth's wind. But just when you thought you understood the limit, a new debate emerged. Because this measurement was taken about 100 feet above the ground using radar, some meteorologists argue it shouldn't count as the official ground level record. The official surface record technically belongs to Mount Washington at 231 miles per hour, or Cyclone Olivia at 253 miles per hour, measured by traditional anemometers. This leaves us with a profound mystery. What was the actual speed at the very dirt level of that Oklahoma tornado? Did friction slow it down, or did it strike the ground with the full 318 miles per hour force? This matters because understanding these hypervelocity subvortices directly impacts engineering. By studying how these extreme wind pockets form, structural engineers are currently redesigning how we build storm shelters and skyscrapers. This research directly influences how humanity will survive the increasingly volatile weather systems of the next century. The good news is that tracking technology has advanced massively since 1999. With next-generation dual-polarization radar networks, we can now spot these deadly subvortices earlier than ever, increasing warning times and saving thousands of lives every year. It proves that even when nature breaks its own rules, science is right there to figure out why.